So the homework was okay, right? It's, you know, it's something new that you might not have seen before, but once you see it, it's all makes sense. It's very logical and methodical. And it's a very useful tool to be able to do implicit integration in time, because you're not, you know, crippled by this very severe delta t restrictions. Okay. Any questions on the homework or anything in general? Okay. So today, the next project that I want to give you will be on advection, pure advection. So you will take a look at how, you know, a scalar profile gets advected by the velocity field, and how a rotating velocity field stretches and deforms the scalar field. So it's a very useful thing to take a look at. And after that, the next project will be solving the full Navier-Stokes equation. Okay. All right. So yeah, last time we saw how we can actually break up the Navier-Stokes equation, the momentum equation, into small parts, and that's called the pressure projection method, and that helps us simplify the computation a lot, as well as it helps us ensure that the velocity is divergence free, right? So just as a recap, we had the Navier-Stokes equation, the momentum equation. Okay, and we said that we can use time splitting or fractional step methods to solve individual parts. So step number one might be advection. Do advection individually, which means del u by del t equal minus u dot nabla u. Okay, and here your input will be un. Your time step, if you use Godunov splitting, will be delta t, and the output will be u star. Okay, and this you probably have in your notes. I'm just doing a quick recall. So, and the next step might be you say, okay, I will do diffusion, which means, let me quickly do it. Let's see, so it's u star star minus u star over delta t equal u nabla squared u star star. Okay, and the final step is always pressure projection. Pressure projection, okay, where we say u final n plus 1 minus this intermediate velocity is the pressure term. But at n plus 1, okay? And we said, okay, we don't know this pressure, and we will compute it so as to enforce divergence-free un plus 1, okay? And we did that by taking the divergence of the whole thing. Okay, which basically gives us the pressure Poisson's equation. Rho over delta t nabla dot u star. Okay, and at this point you see that the right-hand side is known. It's just the intermediate velocity we have computed after doing advection and diffusion. And you should also keep in mind that there's a lot of disagreement among researchers about what this P means. Is it the real physical pressure, or is it sort of a pseudo pressure that you're using to, you know, make your velocity divergence free? Okay. So for me, I don't know whose side to take. So I just say this is a good variable that helps me attain continuity. Okay. But is it really physical pressure? Yeah, see, it's a little confusing. So let's just keep that in mind, okay? So some, yeah.
On step 2,
Yeah.
on the right-hand side, is it U star star
Oh, no, sorry, yeah, this is U star.
Okay. Because that's what the result is.
Yeah,
Okay.
sorry. So yes, you're correct. You do advection, you get the result at U star, and you use that as your input here. Yeah, that was a typo. Thank you. Let's see. Okay. Okay, so some researchers argue that this Pn plus 1 is a pseudo pressure variable. Okay, and just keep that in mind. I still don't know whose side to take. So, okay. All right, so now the question is, how do we solve this Poisson's equation? And you've already been, dealing with this Nabla squared operator in terms of temperature when you have been working with the heat equation. So the discretizations that you saw, that you used with the heat equation, we can use the same discretizations now. Okay. So I think it would be useful if we start with a 1D problem, then go to a 2D problem. Because in 2D, the matrix that has to be formed becomes immense. And in 3D, it's a nightmare. So let's actually start with a 1D Poisson's equation. Let's start with 1D Poisson problem. Okay. And I will take the same problem that you have been doing, you have been solving in your homework. Let's see. We will say del temperature over del time equal kappa plus sine 5x is, I think, sine 5x is what you have. Okay. But now we will say we are interested only in this. We are only interested in steady state solution. Okay, and whenever we want steady state, that means any del by del t can be set to 0. Fine, so we have 0 equal kappa del 2t over del x squared plus sine 5x. Okay, so should just have written del 2t over del x squared equal minus 1 over kappa sine 5x. Okay, so do you know how to solve this? If you forget about numerical methods, can you solve this?
Double integrate.
Yeah, integrate twice. Right? Okay. All right, let's do it. So let's see. Let's integrate twice. Okay, and this is something else I didn't understand when I was starting out with numerical methods. Why do you need initial conditions and why do you need boundary conditions? Okay, and so let's integrate this and then it will become clear why exactly we need these boundary conditions. Okay, so let's see. We have integral of f to b or x squared dx. No. Dx? No, not dx. Yes, dx. Well, integral minus 1 over kappa sine pi of x dx. Okay, so we get dt by dx equal cosine plus, yes, plus 1 over 5k cosine pi of x. Is that right?
There's a constant.
Yeah.
There is a constant of integration missing,
Yes.
right? There's a c1 missing. All right, so let's integrate again. So we get t equal 1 over 25 kappa sine 5x.
Plus C1 x plus C2.
All right. So this is exactly why we need boundary conditions, to figure out what these unknown constants are. Okay. And if so right now we are only dealing with derivatives in space. Initially we had derivatives in time, so you would need an initial condition when you integrate in time. Okay, so to compute C1 and C2, we need to know boundary conditions. Okay, so we have, we might be given that t x equals 0 is 0, t at x equals pi is 0. One more thing, so I cannot tell you arbitrarily that t at x equals pi is 500, okay? This has to satisfy the full thing, right? So if somebody gives you boundary conditions arbitrarily, it might not be possible to get a solution. So ODEs and PDEs are very, finicky in this aspect. You have to specify the problem correctly. Okay. So let's see. So if we use this, let's see, t at x equals 0 is 1 over 25 kappa sine of 0 plus c1 times 0 plus c2. Okay, and we are told this is equal to 0, which gives me c2 equals 0. Right? Perfect. And the other one, t of x equals pi, 1 over 25 kappa sine of pi plus c1 times pi equals 0, gives me c1 equals 0. Okay? So I had picked very nice boundary conditions, which is why I got the two constants go away. So I get finally t of x equal 1 over 25 kappa k cos 5x. Sine. Okay, so we were able to solve this Poisson's equation very easily. What would you do if I gave you a slightly more complicated problem? What if I said solve me the steady state? So let's try a slightly more complicated problem. So let's say I tell you fine, the temperature at x equals 0 is still 0, but now the derivative on the right hand side is 1 over 5k minus or plus. Let me see. Sine, cosine, minus 1 over 5. Let me check that. Yeah. Okay, can you tell me the answer?
Can you go up a little bit?
Can I go up? Like so?
C1 is against 0, C2 is
Yeah, minus it.
1.
Okay, unless I've made a mistake, you will get the same answer.
Yes. Both of them.
And the reason for that is the derivative at the right end is minus 1 over 5k with this sign. Okay? And you know, to use this information, you just use a different, okay, let's do it, okay? So we had, so let's see, we had what was it? T equal 1 over 25k sine 5x plus c1x plus c2. Okay? T x equals 0 is given to be 0, which implies c2 equals 0. Okay? But now del t over del x is at x equals pi is 0, which implies what does it imply? Let's see. What's the derivative here? It's cosine
1 over 5k.
5x over 5k plus c1 equals 0. And so c1 equal cosine 5 pi over 5k. Cosine 5 pi is minus 1.
But it's not 0.
Is what?
No. It's not given by 0.
It's
Yeah,
not 0.
exactly.
Oh,
It's a
wait. It's 5 pi is, yeah.
Minus
You
1.
assume it's not 0, it's 1 over.
Minus 1
5K.
over 5k. 5 kappa.
Oh, I messed up, didn't I? See.
In the boundary condition, you
Yeah, sorry. This is minus 1 over 5. Yes. It was not 0. So, right. So this is 1 over minus 1 over 5. Minus or plus?
Minus. So
Minus.
C1
Ah,
is
yeah.
minus.
this
So
is
then C1 is 0.
minus, right?
Yes.
So this becomes a minus 1 over 5k. So C1 equals 0. Thank you. Yeah, so you know, I just changed the Dirichlet condition to a normal condition, but still the answer is the same. Everything has to be consistent. Here too, I cannot randomly give you this is equal to minus 50, okay? Because it will not satisfy the forcing term. And this is called the forcing term. So this is called the forcing term, or the source term, or the source term. And so if you think about gravitational forces, there, this source term would be like a point mass present in a large domain. Okay? So if this source term is 0, what will the answer be? If the forcing term is 0, what will the steady state temperature be?
Linearly C1x plus C, just a constant.
Yeah, if you say the forcing term is 0, you integrate this twice, you will get a straight line.
Right.
But with the boundary conditions we have specified, everything will go to 0. Yeah, in general, yes, it will be a straight line. For this specific problem, everything will be 0, which is a trivial solution.
Just
Yeah, so it does not matter what temperature profile you start out with, the steady state will go to 0 unless you force it with this. And this is exactly what you're seeing in your own works. The final profile for the temperature looks like a minus sine 5x because the temperature slowly converges to that steady state. Okay. All right. So, okay, but let's see. Somebody does not like to integrate. Okay. How would they approach this problem? You hate integration. What would you do?
discretize.
What?
Discretize numerically.
Yeah, you would discretize this and solve it numerically. This problem, it is feasible to solve analytically. Most problems you will see. Most problems in reality, you cannot do this simple double integration. Okay? So let's discretize this 1D problem and solve it. And then we will discretize a 2-dimensional problem and solve that. Okay? Let's see. If we we could have also solved this. Okay, so let me draw it out again. Let's take, how many nodes should we take? Let's take 2 inside. Okay. So here again, temperature equals 0, del T over del X is minus 1 over 5 kappa. I equal 1, 2, 3, 4. X equals 0. Let's see, L over 3, 2, L over 3. Okay, and find the solution for del 2t over del x squared equals minus 5. Okay, and by now you all must be very comfortable doing this sort of thing. So let's see. For I equal 1, what should I write?
T equals 0.
Yeah, we don't need to solve for it. T equals 0. And remember, there's no time now, so there's no subscript n or superscript n or superscript n plus 1. We only care about the equilibrium solution. I equal to yeah. You've done this in your homework just 2 days ago. Sort of, without the time derivative, you have the same thing. Right? How did you discretize it? Okay, so you have to discretize this second derivative? Oh, yeah, go ahead.
Yeah, I was just saying. Yeah, I was just saying the second derivative of it. Yeah.
Right.
Ti plus 1 minus 2 ti plus ti minus 1 divided by delta x square.
Yeah, so this is exactly what you have seen, and then what goes on the other side?
The right hand side minus sine phi x.
5x. So instead of x, we can put what is x at 2, right? xi, x2, and this is equal to L over 3. Does it make sense? Okay, okay. Yeah,
Then we have to put the left hand side as well as 3, 2, 1.
I'm sorry, what?
Isn't it? The left hand side also has to be put as t3 minus 2 t2 plus t1.
Oh, yeah, sorry. I said I equal 2. Yes, exactly. So let me just write that down here. Okay. So it's t3 minus 2, t2, yes, plus t1 over dx squared equal minus sine 5 pi over 3. Right? Length is equal to 5. That's given. All good? Okay. See, once you're familiar with the basic procedure, you can solve any PDE, no matter where it comes from. Okay. So let's do the same for I equal 3. This will become t4 minus 2t3 plus t2 over delta x squared equal 10 pi by 2. Okay, and for I equal 4, let's see, what happens at I equal 4? Should we write the same thing? t4 minus 2t3 plus t1.
You should write first order.
I should what?
You should write first order.
I should write first order, but first order approximation for the second derivative?
Nope.
Okay. So at I equal 4, I must use this condition that's given. So I cannot just use the governing equation. That's the point of boundary condition. The boundary conditions, you cannot just solve the given PDE. You have to enforce the boundary conditions. So for I equal 4, you said I should use first derivative. So let's see, what would you want me to use? What should I write?
T4 minus T3.
T4 minus T3.
Parallax.
Well, minus sine 20 pi over 3.
No.
No.
Beta to t.
I was just checking that you were aware. Okay, so yeah, at I equal 4, if the temperature was given, we wouldn't even solve for anything. But the temperature is not given. The temperature gradient is given. So we do actually need to solve for T4, the value of T4. Okay. So with this very simple problem, now we have a matrix that we can form. Let's see, what is the matrix? Okay, what goes in here? Oh, okay. What goes in here?
T2,
T1, T2, T3. Is that right or wrong?
No, T2, T3, T4.
Can I go?
Since T1,
T1 is known, so
Yes.
T2,
T2,
T3, T4.
T1 is 0.
Yeah, T1 is known, we don't need to solve for it. So we go, as you said, T2, T3, T4.
Yep.
Okay, and on the right hand side, we will just put these right hand sides, which is, let's see, a minus sign 5 pi over 3, minus sign 10 pi over 3, minus 1 over 5 gamma. Okay, I just wrote what's on the right hand side. Okay, so now let's see what happens inside the matrix. Let's do the last one first. So what goes in the last row?
0, -1, 1.
0, I will write it down and then you should explain to us why. Okay, I mean it's obvious, but yeah, go on.
Yes, third equation T2 is 0.
Yeah, here, right?
Yes.
There's no T2, so T2 times 0 and
T3
times
-1.
minus 1.
And delta x is pi, right?
Delta x is not pi.
Pi over 3.
Pi by
So we
3.
should move it to other side.
Yes, I should put a delta x over here times delta x. Okay. Where delta x is.
We should
It's
separate
delta
it.
x for the last equation and delta x
Ah,
squared.
yes, you're right. Not sure. Wish I'd done this in here. Okay. So there's a delta x over here, but there's a delta x squared over here, right? So delta x squared. Thank you. Delta x is pi over 3, not pi, because
We divided by 3 cells.
yeah, we have divided our rod into 3 parts. Okay, so that's a delta x squared sine 5 pi over 3 minus in front. Again, delta x squared 10 pi over 3 minus, and that's here. All right. Okay. So what happens in the other two?
1 minus 2.
No, -2, 1, 0.
0.
No,
So I am talking about the first row.
second one.
The second one is okay.
I'm sorry, what?
It's okay, okay.
Okay. Let's see. So yeah, this should be good. Let's see. Yeah, T4 times 1 is here. All right. Good. Let's see. What happens for I equal 1?
2.
Okay, you said 2 minus or plus?
Minus 2, 1, and 0.
Okay. So something got messed up.
So there is a T1, but it's known, right?
Yeah. So this
So we can put
T1.
it on the other side.
Not T1, 0.
So yeah, the T1 goes over
Goes
here.
over there.
Uh,
T1 over delta
It was
x
0, I
squared, or it's all times of the delta x.
no, it's not all times. So see, you
Oh,
take
yes,
the
yes.
delta x squared there.
Minus.
So yeah, the known stuff goes on the right hand side, and that's why the T1 arrives here. Luckily it's 0, so in this case it will not make too much trouble. So in general, the Poisson's equation, when you solve it, gives you a tri-diagonal matrix. So you have the main diagonal, you have the upper diagonal, and the lower diagonal. And for all the inner nodes, for the non-boundary nodes, you will keep getting this thing repeated, -1, -2, 1. So, let's see. So let's see, if, where? This tri-diagonal matrix, and here, I mean, it's a 3 by 3, so tri-diagonal doesn't mean much, but is generally but not this one. Okay, so let's say a tridiagonal matrix is generally what we would need to solve. Need to form to solve the Poisson equation. So in general, it looks something like this. So you get minus 2, 1, 1, minus 2, 1, 1, minus 2, 1, 1, minus 2, 1, and you keep going. Okay? And everything else is 0. So you get these 3 non-zero diagonals. Okay, and the first row, so first row and the last row, these depend on the boundary conditions. First and last row can change depending on the given boundary conditions. The inner ones almost never change. Okay, so yeah, if we just go back to our simple 3 by 3, we see the first row looks similar. Second row looks almost the same. The third row is quite different because we had a Neumann boundary condition. If we had the Dirichlet boundary condition, we would again have a 1 over here and a minus 2 over here. And the t end would go on the other side. Okay. Okay, so this is a very simple matrix system. Poisson solve should be very easy, right or wrong? We just form a tridiagonal matrix and we solve it for any problem. Fluid mechanics, gravitational forces, anything. So this very simple form works only when we have these very simple boundary conditions. And we are only working in one dimension. Now I will do a crystallization in 2D and you will see that how complex this becomes. Just in 2D, and then you can imagine in 3D, it's a nightmare. Okay. So when we see, okay, that's fine. All right. So if I give you Dirichlet boundary conditions or Neumann boundary conditions on both sides, or one side Dirichlet, one side Neumann, you know how to solve it. Okay? That's exactly what we did today. That problem now is just to go into higher dimensions. Okay. So let's go back to our pressure Poisson equation. Let's go back. Poisson equation. But in 2D. Okay, so the general Poisson equation we need to solve is nap plus square p equal t. Okay, in 2D, what does it become?
Del square p by del x square. Del square p plus del y square. rho by delta.
Dou u star star by dou x plus dou u star star by dou y. Alright.
Okay, so again, there's a difference between u vector and u component, v component. Okay. Yeah, you were saying. Okay, all right. Okay, fine. So what do we do now? How do we solve the Poisson's equation? Remember, you've already done advection and diffusion. You know what u star star and v star star are everywhere. What do we do next?
Discretize.
Discretize. All right. So let's discretize this. How do we do it?
Then the second order discretization in x.
In x, okay? So it's p something minus 2p something plus p something.
We'll have to use I and j.
We have to use I.
Plus
I
1.
plus 1 and j, I and j, and I minus 1 and j. Delta x squared.
Okay, second term becomes
P
Pi and j plus 1 minus 2pij plus pi and j minus 1. Delta y squared. What is this? So ui plus 1 and j star star minus uij star star. You want a second order?
yeah, let's do the second order.
Minus 1 and j star star over 2 delta x.
Was there a question from Mugabe?
No, I mean, I just say that there should be a, say, time component for the use. That should be
Okay.
n plus 1 of that minus n of that, because there's a delta t outside.
So, okay. So the question is, should there be a time component? Should we have superscripts where we have n and n plus 1? Okay, thank you. I should have pointed that out. So what's the answer?
No. This is a steady state equation, right? What is it?
This is not a steady state solution. We're solving the Navier-Stokes equation, the momentum equation, right? So there is a delta t over here. That's exactly what he pointed out. There's a delta t, but where's the n's and n plus 1's?
This is why we call it pseudo pressure.
This is why we call it pseudo pressure? No, not really.
Not really. Okay.
But that's a very valid question. Why are there no n's and n plus 1's? Do you remember what this star star is?
No solution.
That was
It's the intermediate solution, right? Let me bring back the first page. So see, that's exactly where n and n plus 1 went. So you start doing advection first. So let me write out this step. So it's u star minus un over delta t equal minus un lambda un. Okay. So when you take un and solve this, you get a u star. That's the first intermediate velocity. You take this u star as your new answer and solve diffusion, you get u star star. And that, the second intermediate velocity, goes into the pressure projection term. equation. Okay? And here we used nabla dot un plus 1 equals 0. Okay? We used this condition to get the Poisson's equation. Okay, so there's no explicit n plus 1 or n on the u because it's the intermediate solution. We are still doing the time stepping, so we haven't managed to go from n to n plus 1 yet. Does this make sense? Does this answer your question? Okay. Is that clear? Perfect. So let's go back to the pressure. So we have the U star star, which we know is intermediate. Okay, let's see, what else? What's next?
Ej plus
V.
minus. Ej minus.
Okay, all of the right hand side is known. Let me call this a, what should I call this? F of I, comma j. F I, comma j. Right? Okay, so right hand side is known. What is not known are these p values. The pi, any of the p's on the left side, they're not known. But now it's the same exact problem as our temperature in 1D. Right? When we have this temperature equation, there's an Fi function with index I, and there's all the unknown T values, temperature values. Same thing here, exact same thing. Mathematically, it's identical. Now we are doing it in 2D, you are doing it in 1D. Okay, so let's see. Now you can already see that the matrix system we need to form here will be a little bit of, it'll be a little long. So let's see, let's say that we have delta x equal delta y equal h. So you can do this, right? I mean, when I give you a rectangle to discretize, you can say that I will do it such that all my discretization gives me perfect squares. Right? So this is just saying the discretization is your choice, so you get to decide this delta x and delta y. Okay, and this will just make it easier for me to write out the matrix. Fine, so if we rewrite this with this new information, what we get is a pi plus 1 comma j minus, no, plus pi minus 1 comma j minus 4 pi comma j Okay, I haven't done anything. I have just taken this long thing and said delta x, delta y are equal. So this becomes times h squared. This is good. And now we have basically the same thing as we had in temperature. We have the unknowns on the left side and the knowns on the right hand side. In 2D, we have to deal with 5 of them at the same time. In 1D, we had to deal with 3 of them. So we had a tri-diagonal matrix at that moment. What will we have now? We will have 50 diagonals. We will have a pentadiagonal matrix, okay? We will have 5 diagonals because there are 5 elements. Sorry, I beat you to it. Okay, so let's see. For knowing what the pressure at Ij is, you need to know your neighbors. Okay? It's all interrelated. So if I want to find out pressure over here, I need to know okay, so I think I mentioned this before. So we have a 5-point stencil. For solving the pressure at each point, you need to know the 4 surrounding points. And that's exactly what this equation is saying. Okay, let's form the big matrix. Let's see, I will need a lot of paper. Okay, so, before we form the matrix, okay, let's say we have nx points in x and ny points in y. Okay, so what are the unknowns? Okay, I will zoom this in. J equal 1, J equal 2, J equal 2, J equal 3. Okay, so in temperature, when we were looking at the 1D problem, we only had to care about these lines. Now there's NY lines to worry about in the Y direction. Okay, so can we start forming our matrix? Sure. All right, what should the first row be?
Boundary conditions.
Yeah, we need the boundary condition. I haven't told you the boundary conditions yet. So let's see. Let's say, how many boundary conditions do we need?
The unknowns do we have? 4?
4. Another answer? Once more?
2 for x, 2 for 1. 4.
4. Yeah, 4. You need 4 boundary conditions. Why? If you go back here, if we had the second derivative in 1 dimension, we needed 2. Now we have 2 derivatives, we need 4. Because there will be 4 constants that we will need to get rid of. Okay. So we need 4 BCs. We need 4 BCs in total. Okay, so let's start with just the lower and left arms. Let's see. So let's see. We are told what should we pick? Let's pick this del P over del Y is at Y equals 0 is 0. Okay, physically this means the pressure does not change when we cross this boundary. Okay, so physically this implies
No penalty.
pressure does not change in the y direction as we jump over the lower boundary. Okay, let's take another boundary condition. Let's see. Second BC. Second boundary condition given is del p by del x at x equals 0 is 5. What does this mean? Basically, what does this mean?
So the rate of change is constant.
The rate would be with time, right? So we're talking about spatial derivative. So let's saying the spatial derivative on this whole boundary is some given constant.
So it increases linearly.
Pressure increases linearly. Yes, yeah, pressure would increase linearly, but
Just at the boundary.
only at the boundary.
On the boundary.
Yeah, so we don't really get what's happening inside the domain. Think of a water hose, right? Or any pipe. Why does water move from one end to the other?
Convection.
Convection, yes, but you need to do something before that.
We pump the water.
You pump the water.
Or pressure.
Yeah, so you see, that's exactly what you're changing. You have a pump that's working on one side, that increases the pressure on one side. There is a pressure gradient established at the inlet of the pipe, and that's why things start moving. Okay. So physically, this would be the equivalent of saying you're imposing a pressure gradient, which can cause the fluid to move. So physically, imposing a pressure gradient will cause the fluid to move. Okay? All right, fine. So physically, we know what that means. Let's come back to forming our the boundary, the matrix system. Okay, so let's form the matrix. If you need me to move the paper, let me know, because it's cutting out. Okay, let's form the matrix. What should I do? Anytime you want to form the matrix, what do you do?
The variable coefficient, no, then
You need to know how many unknowns.
on how many unknowns do you have, then write the coefficient.
Yeah, you have to figure out which points are the unknown values. So, all right, let's see. The first point, is it unknown or known?
No.
No.
Okay, the answer is first point is known. Is that right or wrong?
What was the boundary condition? It was, sorry. No, it's not known.
It's not known. All right, so which one is the right answer? It's not known, right? The pressure is not known. The derivative is known.
Yeah.
So, okay, we can use that information. Fine.
Because it should give us two derivative and two Neumann boundary conditions.
You want the other two conditions as well. Yeah, I have not given you what the right and the top boundary are. Okay. Technically, yes, I should give you the two Dirichlet boundary conditions. Okay. Because if you specify Neumann on all sides, that's not a well-posed problem. Yeah, think about it. You know, it's okay. Again, what do Dirichlet and Neumann boundary conditions mean? Dirichlet boundary condition means I'm holding this side at 100 degrees. So a Neumann boundary condition might say, if this is equal to 0 on the other side, what will happen to the temperature in the rod?
There is a linear conduction.
There's an equilibrium, yes? What were you saying?
If this Neumann bound, you said no Neumann boundary condition equals
0 Neumann boundary condition.
It won't change all around the line. I mean, all along the line.
Yeah, if I specify this nice 0 Neumann boundary condition on one side at 100 degrees here, slowly the temperature will increase, right?
Deep.
Dip.
Two constant temperatures from two sides.
That will be a straight line.
He said that the second side won't change, so it will decrease
Yes, that's true.
Decrease.
A line,
It's linear.
not line.
Okay, wait. All right, so let's take a small side. Okay. So if you have a rod, right? And I say I will hold this side at 100 degrees centigrade. And this side, you know, del T by del X is 0. Meaning heat is not allowed to flow out or in. What will happen to the temperature in the rod? That's exactly what we were doing with the pen. Initially everything is 0. Suddenly you put this to 100 degrees. What will happen? Physically.
The temperature will increase going through the rod.
The temperature will increase.
The remain constant.
Until
Say.
And then it will be 100 degrees.
Yeah, so the temperature will increase and then it will be constant at 100 degrees until it, you know, all grid points are at T equal 100. Make sense? But now, you know, if I say, here I will insulate it, and on the left side, I will say del T by del X is -1. First of all, what does this -1 mean?
It's not possible.
Del T by del X is 0. With my mind switched off, right? And on the other side, del T by del X is -1.
So there is heat is going out, for example, but the heat is constant in the boundary.
Okay, the side heat is going out.
But there is no input.
There's no input. What do you mean?
And the right side is isolated,
That's isolated, fine. There's no problem.
and left.
not isolated.
It's what?
It's not isolated.
Yeah, so this is like as if you are cooling the side at the rate of -1 degree per
There's a heat loss.
L per meter. Yeah.
Yeah, there is no conservation of temperature. Okay. So I was thinking
Conservation of
of
This okay, let's do the same with the positive, right? Del T by del X is 0 and you have positive +1. Del T by del X is +2, right? Then that means you are inputting energy from this side all the time. And eventually this will go supernova because you keep giving energy and nobody's allowed to leave on the right hand side. So yeah, fusion will start happening soon. Okay? So this problem is not well posed. If I say both sides equal 0, then yeah, everybody's happy. But that's only in that very special case. If both sides del T by del X is 0. So if I give you Neumann boundary conditions on every side, that's not a well-posed problem. Exactly because of this.
But this is possible, right? This is but not well posed. I mean, is that different term?
No, it's not possible. So remember, we're talking about the steady state solution. There will be no steady state solution because you will keep pumping in heat over here. So you will go to infinity. Okay, so so that's why you mentioned, yeah, I gave you two Neumann boundary conditions. I also need to give you two Dirichlet boundary conditions. So let's say pressure is 0 on the top boundary and on the right boundary. But for forming the first few rows, we actually will not need the right and the top boundary conditions. Okay, so let's form the matrix for, let me say, okay, I equal 1, j equal 1, that's right. We're given that dp dt by dx at x equals 0 is by dp by dy at y equals 0 is 0. Okay, so what should I write? Do I need to write something? Is everything known? I don't need to write anything.
I will say.
Yes, right. I mean, discretize it for the boundary condition.
Discretize it for the boundary condition. We don't use this
No, not
discretize.
that one. Like P.
Alright. So, alright, what should I write?
P, P2 minus P1 over.
Is there a question?
Yes.
No. Alright.
No.
I'm asking.
P2 minus P1 over
Delta X
delta x.
equals to 5. 7.
Okay, alright, now go ahead. In Volcano, yes.
P2J, isn't it? There are the two P2J and P1 minus P1J.
Better?
No, J. Is it? It's P2J minus P1J.
Why?
J could be anything.
No, I said J equal 1. Here.
Oh, okay.
Go ahead.
Why don't we use ghost cells for this equation and use second order discretization for, for del x, and our error will be second order, not first order.
Okay, so the question is, we have our real boundary. Why don't we create ghost cells? Ghost cells, if you remember, we create fake cells over here and put, mathematically correct data in there. What would you put in there? These ghost cells don't have a value. You give them the value. What value would you give them?
We said mean values exist.
You're making an assumption there, right?
Yeah, I'm making an assumption.
So yeah, you're feeding something and then taking the second order difference, but that in the end will end up being first order. You are populating these with linear extrapolation, for instance.
Okay.
Okay? And if you take the center difference with this linear extrapolation, and if you do the Taylor series expansion, you will get its first order accurate.
Which error is the considerable? No. Which one? Which first order? Because in both circumstances.
No, it's worse actually, because you have made an assumption that it's linear extrapolation and you have the discretization.
Okay.
Okay? All right. So, yeah, I mean, you could have tried something more sophisticated, but you don't have enough data at the boundary to be able to try something better. Okay? So your limit, if you were lucky, you would have periodic boundary conditions. In that case, you would copy the top boundary into these cosets, and then you don't have an error. Okay. But right now, we don't have periodic boundary conditions, so we must use one-sided differences, either 2 points or 3 points or more. Okay. So that's exactly what we have done here. We have used a one-sided difference to approximate the dp by dx. Yeah, dp by dx. Okay, is this the only thing I could have said?
A second order too, right?
A second order, one-sided. Yeah, but then there would be a 3 and a 4 something. You always have to use one-sided, so there would be a E3 and E2 and E1. You cannot go on the left side. Okay, so all right, here you made me discretize dp by dx for I equal 1, j equal 1. Is this the only possibility?
You could do it by
Oh.
delta y. The
You
y.
could even do this one, right? So at I equal 1, j equal 1, both of these boundary conditions are valid. You're free to use either one. The person who has formulated the problem, they have to make sure that these will lead to a good answer. They cannot just give you these things arbitrarily. Again, remember what we did with our, our metal rod going super. Okay, so you could have taken this choice, or you could have said E what? E1, comma 2 minus E1, comma 1 over delta y equals 0. Does this make sense?
Why not either of these two? Yeah. Why not simultaneously both of them? I mean,
You want to add the two?
yes, both of them at the same time, because I mean, my question is, do we have the enough equations to solve the domain later, maybe after?
Yeah, so see, there's nothing different happening from our original one-dimensional case, right?
Yes.
Here we had enough equations to solve as long as I was given 2 boundary conditions.
Right.
Now, the same thing, I will have enough equations to solve as long as I'm given 4 boundary conditions.
So 4 boundary conditions, and then
In total, over the full domain, over the full rectangle.
So we don't have to include both of them in the matrix.
Yes, you do not need to include both of them. You can pick
either of
either of them, right? So let's take this one. Okay. For I equal 2, j equal 1, what goes into the equations?
to the equation. Yeah, just plug in I2 and J1.
Plug in what?
I equals to 2, J equals to, so it's P3 and 1 plus.
You want me to plug this? No. See, I equal 2, j equal 1 is still on the boundary.
Ah, sorry.
So we have to use the boundary, which is y equals 0, this one. So we have E a 1, comma 3 minus P 1, comma 2 over. Wait, what? No. Sorry. E2, comma 2, E 2, comma 1. Delta y is 0. Make sense? Yeah, so see, it's already getting very cumbersome. So for the first whole line, you would have something similar. Okay? Let's see. I've run out of paper. And I'm going to run out of time. Okay. Yeah, we only have like 3 minutes, so we can do that next time. It takes a while to get the whole matrix out, but we will continue from here. Okay. All right, and I will try to put up the advection project today, at least by tomorrow. Okay. So yeah, let's stop there.
We had an exam right before this.
I know.
Math
It's okay.
was the first exam. It's a little stressful.
Don't worry.
It wasn't bad. It was a lot easier than I thought it was going to be, actually. But I didn't know that last night or the night before.
You're like Jeremiah.
I sleep. I don't stay up the whole night, but
I was up till 3.
I went to sleep early as well.
Good academics exams are pretty easy. Just give you some tricks.
Yeah.
Okay.
You know, I still have nightmares that I forgot to wake up for an exam and I'm 2 hours late.
That's
me.
my
Yeah.
biggest fear. That's
When I was
awful.
stressed, I was solving questions in my mind when I was sleeping. And when I get up, I said, I solved this. But it's been proven 4 days, 5 days after the exam, you know?
Yeah.
Too late when I solved this in my mind.
Exactly.
At least you don't have an exam in CFD.
I know.
Try.
It's a blessing.
Thank you.
Try. It
You
will
want
end,
to?
it will end probably after 6 hours, you know?
Are you registered in the course?
No.
It would
Then
be the,
you.
it would be the first time.
Good luck with it. We have time?
Oh, yeah.
I felt real bad because I didn't pay attention to a word. And normally I like input all the time.
I was zoning out. I'm just tired.
How was the test?
It was great. Surprisingly.
It wasn't great, it was an exam, but it wasn't
I
as
passed.
difficult.
That's
as
all
I
that
thought
I
it
care
would be.
about.
Yeah, we both passed.
Nice to see you, Nicole.
Nice to see you as well, Gordon. I wore my hat hoping you would recognize me.
You need your,
I'm just kidding.
Nicole, you need
You
your
need
shirt.
Need a little bit more than your hat.
Exactly.
Let's see, what's next?
I wore my hat because I couldn't shower this morning.
Go on in here.
So James,
Yeah.
do you want to start this CFD project tomorrow?
I had to do a machine learning project.
Need to do what?
Machine learning project.
Yeah.
Actually.